Okay, question. You had a problem where you knew that n of ty dt plus quantity y squared minus 3ty dy equals 0. You're given that this is exact. You want to find n of ty. Well, you just apply the condition of exactness, which is that the the y derivative of this has to equal the t derivative of this. Why is this? Again, because this expression, if it's exact, came from some function whose differential is this. So the t derivative of that function times your dt is this. Here's your y derivative of that function times dy. So when you take the y derivative of this, it's got to equal the t derivative of this, because the y derivative of this is the ty derivative of the original function, and the t derivative of this is the yt derivative of the original function. They have to be the same because the order of partial differentiation makes no difference. Okay, so these are exact. It follows then that the y derivative of n equals negative 3y, which is the t derivative of this function. And then n is just your general antiderivative of this, but your general antiderivative in a function of ty, your general antiderivative with respect to y, the constant is really a function of t. So your n is negative 3y squared plus any arbitrary function of t. Okay, well, next we look at drag for a drag force proportional to the square velocity. Now, if we just have the only force, if the net force is the drag force, which is proportional to the square velocity, then you have this equation, mass times acceleration equals your drag constant times v squared, but it's going to be negative because the drag is going to be in the direction opposite v. So you end up with an equation that's very easily solved. You end up with v equals 1 over c plus kt over m. That's a rational function. It's a basic form 1 over 1 plus x, and if we understand the most common functions, graph of 1 over x is the white graph. The graph of 1 over 1 plus x is just a graph of 1 over x shifted 1 unit to the left. Now, if you do a change of variable to where this matches this, whatever your constant c happens to be, it's going to look like this. You're going to shift this thing to the left, and you're going to end up with a solution for t greater than 0 that approaches 0 like so. And that's kind of exactly what you expect for a drag force that decreases with velocity. So you're slowing down more and more slowly, so your velocity function will look like this. Okay, now, another situation, you're following with this sort of drag force, which is fairly typical once you get up to certain speed in a free fall. Okay, so we have this equation. It's very straightforward. Your velocity is down, your mg, force of gravity, is down. We'll take the positive direction as being down, so that our equation becomes this. The drag force, negative kv, kappa v squared, being in the direction opposite mg. That does make a difference. If the object is rising, well, we'll see that that gives a very different looking solution. Okay, well, anyhow, we have then simple rearrangement of the equation, and we go through the details. And I use alpha equals kappa over mg to abbreviate what we get here. Now, this has got to be done by partial fractions, because you have a difference of 2 squares, essentially. You factors a difference of 2 squares, and you end up with this partial fraction decomposition. It turns out that for a difference of 2 squares, a and b are always going to be 1/2, but you work that out. So you have a over 1 plus alpha v plus b over 1 minus alpha v has to equal 1 over 1 minus alpha squared v squared, where alpha is the square root here. The square root of this, okay, square root of k over m. And it's k over mg. I also factored out the g here, and the details of that are simple enough. Hopefully everybody understands how that works, but you can easily check it out. Okay? Now, we complete the solution here, and we just run through the details. Okay? The two integrals will be dv over 1 plus alpha b, dv over 1 minus alpha b. We'll have 1/2 that came from the partial fractions, and that's going to be out here on the g. And this is, I think I read it as dv because that's what it looked like, but it's alpha v. Still using the shorthand for alpha just to make it look simpler. So we end up then with the natural log of this, and I'm not going to go through the details of that. It's very common, very straightforward, something you do a lot when you're solving partial, or when solving differential equations. And we end up with this, and at this point I'm kind of questioning it because I had solved it earlier, but it worked out. So we find if the natural log of this is this, then of course this is e to whatever this is. And we know that e to something times t plus c breaks into e to the c times e to that something times t, giving us a positive constant out in front of e, and that's going to emerge in this step. We just do the algebra to solve this. We multiply both sides by 1 minus alpha v. We get this. We rearrange the equation. You can rearrange it. You can verify that it rearranges to this form. We got to get all our v terms on one side. And when we do, everything factors the way I say it does here. And we get this. And then we verify that as t approaches infinity, the velocity approaches some terminal velocity. Now actually, as you approach terminal velocity, you'll get out of the realm where your drag force is proportional to v squared. So really it won't quite exactly happen this way, but still this is the approximation we get. You'd have to break it into two functions, and you'd have to know where velocity goes from being squared to being the first power, and it doesn't just go suddenly. There's a transition phase, and it gets very complicated. So we're doing an oversimplified solution here, but in any case, we can see that as t approaches infinity, one way to look at it is this e to the 2 alpha gt is eventually going to get huge. Well, if this is huge, well, this is also huge because this is equal to this, and subtracting one from something huge or adding one to something huge doesn't change it much. So this is clearly going to approach 1. Now formally, you would divide every term in the numerator and denominator by e to the 2 alpha gt, and then you would look at what you have in the numerator and in the denominator, and you would very easily conclude that the limit has to be 1. And then of course that's times the 1 over alpha, and that approaches 1 over alpha, remembering that alpha was the square root of k over mg, then 1 over alpha is going to be the square root of mg over k. And we check the units of that. M would have units of NSI, it would be kilograms, meters per second squared, and kappa would have the units that are necessary to multiply v squared in order to get a force. And it follows pretty quickly that alpha would have to have units of NSI, would be newtons over meters per second quantity squared. And you simplify that, you find out that the units of the square root of mg over k is meters per second. Okay? And so that gives you velocity, so we check the units, everything works out. And we should also check the units over here to see that the units of alpha times g are reciprocal seconds, because if they aren't, we don't have a pure number as an exponent of our exponential. Now, things get even more fun if you have a rising object under this sort of force, and now the kappa v squared and the mg are going to have the same sign, because from this diagram, if v is up, then negative kappa v squared is down, and then your drag is down and your gravitational force is down. So both of these will have the sign opposite that of v. So we could write the equation like so, and that, we could actually write it with pluses there too if we really wanted to. But after rearranging and doing a couple of changes of variable, which you want to be sure you do. Well, you first recognize that this is very much like a 1 plus x squared in the denominator. Like if you factor out g and do a change of variable, here's the change of variable you use, and here's what you would get. So that's going to give you an arctangent equal to the integral of negative dt, which is negative t plus c. And then we solve. First we isolate the arctangent of this expression, and that would be equal to this, and then we take the tangent of both sides, and we get, well, this is going to be the tangent of all this stuff. So that v would be the reciprocal of this times that tangent, and work out the details, they're easy enough. We get this. And if we look at the graph of the tangent or of a negative tangent and shift it, we see that we could get something that would maybe give us the right expression for the velocity, which approaches zero. So you might have this branch of the tangent function after you shift it, and you would have this function, which of course approaches zero at a certain point. And that's where everything would stop, because of course when you stop rising, you start falling, and when you start falling, you're back over here. Okay, now again, all this ignores the transition from a squared turbulent, a turbulent situation where you have a proportionality to v squared. That can even go as v cubed if you're going fast enough. To the laminar model where you have just the proportionality to v, which we didn't really look at today, but we looked at before. Also, we here made the comment that we want to contrast all this behavior with what happens if you have linear drag. Then you have an exponential approach to a limit. And that's all very straightforward.